Okay, the first thing that we have to do today is talk about how we deal with the voltages and currents in an AC circuit. So yesterday we talked about um, how the current.
Alternating current, how it kind of vibrates instead of traveling.
Yes, but I mean specifically that
The electrons vibrate.
I'm talking about the equation now.
Oh,
How the equation was the voltage equals V naught sine 2 pi weird f t frequency times t. No, that was for the current.
that's for current.
Do y'all remember what the V naught was?
I
What
thought
the
it was the initial for some reason. That felt similar.
It's not initial, so I'm gonna erase that naught and make that into a max.
Okay.
So that's the maximum voltage, and the actual voltage is based on this function. And remember, that was because the voltage itself was shifting between the positive and negative versions of its maximum.
Yes, and that's what made the electrons vibrate.
Yes. Yes, the Vmax would be the amplitude of the function, which is in the same place that the amplitude is for a sine function. So we know that. So we also know from when we were talking about DC circuits that the power of the current is equal to IV. So that means that the power in an AC circuit is equal to the current times the voltage. And in this case, the voltage is this equation, so we could say voltage max. Actually, hold on. Before we do that. Actually, let's, get rid of this.
I'm writing this down.
So if we want the actual current because the current will do the same thing, it's just got a more complicated, well, not really that much more complicated, but its equation isn't quite the same, but the current is going to do something similar. We know from Ohm's law that V equals IR, so if we want current, we have I equals V over R.
Yeah.
So that means that, wait, no. Wait, hold on. Yes, so that means that if we have this voltage, we can get the current in an AC circuit. So I could say this is the voltage in an AC circuit, and this is the current in an AC circuit. We would take the same maximum voltage that we could get and divide it by R. That's where that one came from that you were talking about earlier.
Oh, yeah.
So now if we want the power, we have to take the power of the AC current, or sorry, the power of the AC circuit is the AC current times the AC voltage. Yes. And the way your book writes it down, because remember, we can also say that power is current squared times resistance. But we're not going to use that. There are other ways to write this, to write what we're going to write here. But we're going to write it as the maximum current. Sorry, let me put max instead of. Yeah. The maximum current times the maximum voltage over R times sine squared 2 pi frequency t. Well, so we would end up with a sine 2 pi ft times sine, oops, missed the sign, 2 pi ft. So it's this times this, so it's all of this squared. Or it's the result of the sine squared, not. So remember that sine can't exist without something here. So these things are part of the sine. So if we're saying the sine squared, then these things are also getting squared. Kind of. It's like we're getting. Remember that a squared here is like saying all of this squared.
So it's like in the calculator it says sine and then the 2 pi frequency t is in the parentheses.
Yes.
Oh, okay, that makes sense. Maybe we should start writing it like that.
Maybe.
Anyway.
I typically don't write it like that just because it takes more time. And I know how to tell the difference.
But do we know how to tell the difference?
You should.
We are not.
You should get to the point where you can understand it. So, how can you tell the difference between what?
What if it's just
So there are,
sine 2 pi, let's say, and then multiply by
that,
that? Then it makes sense.
well, that's why we write things in front of the sign. So, and that's how we deal with it, by writing it in front rather than writing it behind. So that's why we don't use why I don't use the parentheses, because I'll just write it in front instead of
Makes sense.
parentheses times pi. Okay. So this is kind of a fairly cumbersome equation to deal with if we want to know the power. So typically what we do is we take the average power of an AC current, which turns out we just take half of the maximum current times the maximum voltage. And this is good enough to deal with AC stuff.
No, I'm just gonna put that over 2.
Yeah, you can put it over 2.
That seems like it's important.
But y'all know that this bar means average, right?
I thought it meant repeating.
It can mean repeating as well. So we can get another form of this equation by saying this and splitting up this 2 as the square root of 2 and then times the square root of 2. I'm about to show you why, but do you understand that it can do that?
I'm just gonna do this up.
The 2 is the square root of 2 times the square root of 2. So I've just got square root of 2 in the denominator on both of them. So we end up turning this equation into the average power is equal to I, and instead of saying max, we say root mean square times V root mean square. So the RMS means root mean square. Okay, I need to check something. So Talon just asked, why would you do that? Why does that make sense to do? The reason we want to do this is so that we can actually turn all of the equations that we've previously dealt with into these equations. So instead of talking about V equals I R, we can talk about the root mean square voltage equals the root mean square current times resistance. And the resistance doesn't, because resistance is just a thing. It's constant, whereas these will change. So now we can deal with, instead of going back up here and dealing with the voltage and the AC current as this big cumbersome equation, we can just deal with it as a root mean square. And basically what that gives us is it's kind of like an approximation of the average current and the average voltage. Does that make sense?
Powers and watts.
Okay, this is DJ. I'm going to work out this problem. So we know that PAC equals IRMS times VRMS, and we know our V, which equals 34, and we know our resistance, which is 8, and we can get VRMS pretty easily by just doing 34 over square root of 2, which I got that equals 24 point something, but it's so small that it doesn't really matter. So I'm not going to write it. So we have that. And current, we know, equals V over R. So we can find current pretty easily by just putting 34 over 8, which I got equals 3. No, wait. No. Yes? Yeah, 4.2 equals, sorry, 4.25. I'm getting ahead of myself. Then we put that over square root of 2, and you get 3. Then we just times that by 24, and we get our PAC.
What is that?
That is what we were trying to find, average power.
What is that?
That's a smiley face.
What's the
No, it's 3 times 24. What is that?
Is the,
what's the number?
It results in what number? When you multiply it together.
this, oh, derp, 72. So this is an answer, this is an answer, and this is an answer.
72 point.
And this is a smiley face.
Okay.
This is fun. Can I just do this all day?
You press the
Oh, okay. Oh, no, I can do this. I believe in me.
Okay, so we're going to leave the AC circuits now and just talk about DC circuits in general. Well, we're going to talk about circuits in general. But we need to talk about connecting multiple things at once. Like, if we have a battery, we need to start talking about connecting 2 light bulbs. That's, well, maybe it's a Christmas tree light bulb.
So what is that?
Christmas tree light bulb.
What color is it?
You pick.
Hello.
So we needed to be talking about. Now, I mentioned yesterday that if you're connecting them one after the other like this is called series.
Yes, that's a series. But
So-
if they were like not next to each other, they'd be parallel circuits.
Right. So we're going to say that,
They act as resistors?
yes, anything that is taking energy out of the system, like a light bulb or a TV or a toaster, we can basically represent it as a resistor if we can calculate it simply and reduce it to a resistor.
So we just treat them as resistors. Oh, that's so cool. Okay.
So if let's say that this is R1 and R2, and each time the current goes over a resistor, it loses a certain amount of voltage. So we can say that over this resistor, it has this amount of voltage, and then over the second resistor, it has a voltage too. So if we want to figure out, let's call this the battery itself an actual, just a regular V. So the voltage that's lost here and lost here would be exactly equal to this voltage, or the total, maybe the total voltage of the system rather than, not this V, sorry. The total voltage of the system would be just like if we add two batteries together in series, then their total voltage adds together. I think we've done that before. I thought I remember doing an example like that. Well, it happens. If you connect two batteries one after the other, it's just like one big battery with the voltages added together.
So kind of like that scene in the Lorax where the tree runs on 96 batteries.
I haven't finished
kind of like
the Lorax.
Pushed into the tree.
Sure.
Yes.
Yep. I don't know. So the total voltage of the system is just going to be the V1 plus V2. We know that V equals IR, so in this case V1 is going to equal I times R1, and V2 is equal to I times R2. So the total voltage we can now say is I times R1 plus I times R2. And then both of these terms have an I in them, so that means we could factor an I out. So we can get I times R1 plus R2. So as it turns out, to get the actual V equals IR of the system, all we have to do is add the two R's together. Or so whatever the ohms, like if this is 7 ohms and this is 3 ohms, then we would say V equals, I times 10. So basically what this, connecting them in series means, I should probably write this down. A connection in series, in series, thank you. A connection in series means, I don't know why I can't write. That each resistor gets the same amount of current. And that's why this has this I here doesn't have a 1 or a 2 next to it. They'll have the same resistance, or the same current going through both of them. But the voltage that goes across them is different. And that we can figure out with these formulas to find their different voltages. Oops. So now we have another problem. Okay, so the first thing that I like to do in every problem, no matter what, is draw a picture. So here's my 12-volt battery connected to two resistors in series. where I have a 6 ohm and a 3 ohm. So what we just learned just a second ago was that we can basically turn these two resistors into a single resistor. And all we have to do is add the two resistances. So this now would have a resistance of 9. So the current would be V equals IR. So the current is V over R. So that's 12 over 9, or what is that? 1.3 repeating, or 4/3. And that would be in amps. Okay, and then we want the power dissipated in each resistor. So what we can do is we can say, now we're going to go back to this model, and we're going to say we know that the power equals I squared times R. That's something that we had. We can get that from this equation, and then the P equals I times V. Oh, sorry. If we combine these two equations by plugging V in for this V, then we get R. I think you got it. So P equals this current times the resistance for 6, and that gives us the resistance, or the power for this one. Yes, thank you, I forgot that. Squared, that should be squared, I forgot to write that. And then the power over the second one would be 1.3 repeating squared times 3. So then what does this one end up being?
P1 is 10.14 and P2 is 5.07.
10.14?
Yes.
Now when you typed this in, did you use 1.3 squared, or did you type 1.3 squared? Okay. The book has 10.6, which shows a kind of significant difference than what you just answered. So use 10.3 repeating, or you could actually just type in 4/3. That would give you an exact answer.
Or as close to exact as we can get.
Well, no, if you type this in, it gets you an exact answer. You just might not be able to write down all of the numbers. So 32 over 3 would be an exact answer.
Do we need an exact answer?
If you can get an exact answer, why would you not want it?
Okay. In this situation, do we need an exact answer?
No.
Okay. I know I'm so weird about my feet. I am so sorry.
So the total power would be P1 plus P2, which comes out to be 15.9, or something close to that.